Okay, so today we're going to talk about invariant subspaces. And invariant subspaces, essentially there's applications, invariant spaces have applications to differential equations and difference equations. Okay, so what is an invariant subspace? So if A is a square matrix, then we call a space S that is a subset of the range space of A. We say that this subspace is an invariant subspace if X starting in S implies that AX is also an S. So in other words, it's invariant in the sense that, you know, we start in S, here's S, we start here, and A just kind of moves us somewhere else inside of S. We don't change where we are with respect to S. Okay, so for example, eigenvectors form invariant subspaces. So if I have any particular eigenvector X, then when we multiply through by A, we get lambda times X again. And so this is just a, since it's a subspace, this is just an element of S as well. So any eigenvector or any linear combination, I guess any space spanned by linear combinations of the eigenvectors will be invariant subspaces. Yeah, this is another, I guess just restating what I just said. If you have the span of any subset of eigenvectors, so you have any set of eigenvectors, then the span of those eigenvectors will be invariant, because if we have, any x hat in S will just be a linear combination of those elements. That's what it means to be in the span of those vectors. And then when we multiply through by A, we again get something that's a linear combination of those vectors, so it's in the span of those vectors, or S. So again, any linear combination of eigenvectors is invariant. All right, so now how does this apply to, for example, differential equations? So suppose we have the differential equation x dot equals ax with some initial conditions. And recall that any differential or any linear constant coefficient differential equation can be written in this form. So for example, let me, let's see, I'm going to actually write over here, so I guess I can do this. All right, so for example, if I have y triple dot plus 3y double dot plus 2y dot plus 4y is equal to 5u, let's just say, then I can put this in. So this is a linear constant coefficient differential equation. I can create a state. So for example, let's let x be x1, x2, x3, and define that as, x1 is y, y2 is y dot, or x2 is y dot, x3 is y double dot. So when I take the derivative, x dot, I'm going to get, x1 dot, x2 dot, x3 dot, and that's equal to y dot, y double dot, y triple dot. Y double dot is just x2 from up here. Y double dot is x2, x3 from this line. And then y triple dot is going to be minus 3 y double dot, which is x3, minus 2 y dot, which is x2, minus 4y, which is x1, plus 5u. And then I can write this equation in terms of a matrix, x1, x2, x3, plus vector times u. And so x2 is just 0, 1, 0, 0. x3 is 0, 0, 1, 0. And then the bottom line, we have minus 3x3 minus 2x2 minus 4x1, 1 times u. And we've now written this in the form x dot is equal to ax plus bu, where this guy is a and this guy is b. All right, so again, you can think of this, this process. And how I describe it here, it's not exactly, if you had, for example, a plus 6u dot, this isn't exactly the way you would do it, but you could do something called control canonic form or observer canonic form. These are topics discussed, for example, in a class on linear systems theory or control theory that shows how to put these general equations into a form that looks like this. X dot equals ax plus bu. All right, so let's move back over here, and we say, okay, I guess if in this particular case the b is 0, then let's look at solutions to the differential equation. And the claim is that the solution is e to the matrix AT x naught, where e to the matrix AT is, I plus AT plus 1 over 2 factorial. And recall that the scalar equation, e to the x is 1 plus x. Well, let's see, let's just write it this way maybe. Let's say that e to the little at, the scalar case would be 1 plus at plus 1 over 2 factorial a squared t squared plus 1 over 3 factorial a cubed t cubed a cubed plus dot 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 forever. Okay, so this is the scalar case, and the matrix case is just, as we've seen, you just take that polynomial, instead of x, you put in the matrix A, and we get a matrix function, a function of the matrix. So e to the at is a function of this matrix A, and also a function of time. We can take the derivative of, how do we show then that, for example, this x of t equals e to the at x naught is the solution to this differential equation? Well, we could differentiate, we take this and plug it in and show that it in fact solves this differential equation. So let's go ahead and differentiate x of t, dx dt. And when we do that, we're going to differentiate, e to the at times x naught plus e to the at times the derivative of x naught. And of course, x naught is constant. It's the initial condition. So this is just d dt of, in this particular case, a of t times x naught. So we're going to take the derivative, missing some parentheses here. So we're going to take the derivative then of this Taylor series expansion times x naught. Now when I differentiate each of these terms, so the derivative, and here we're just going to differentiate, it's just a matrix, so we're going to differentiate, what we mean by the derivative of a matrix is we're just going to take a derivative of every element of that matrix. So when I have, the derivative of identity with respect to t, there's no t in here, so we get 0. Now I take the derivative of t is a scalar, a actually pulls out, so that's just going to be the derivative of at is just going to be a. The derivative a squared is a constant, 2 factorial is a constant, so the derivative of this term is just the derivative of t squared, so it's going to be 2t. So we get a squared t 2 over 2 factorial, and then we get the derivative of this thing will be a cubed t squared over, and the 3 comes down and cancels out, and you get 2 factorial, etc., times x naught. And now what we're going to do is we're going to pull a out of each of these terms. And if we pull on the left, then we'll get, what shows up again is going to be e to the at. So x dot is going to be a e to the at x naught. And then you notice that this thing is just x of t. So that's a x of t. So derivative x dot is equal to ax. Therefore, it satisfies the differential equation with these initial conditions. All right, now let's just understand maybe a little bit the, kind of what the structure of the solutions will look like. So let's suppose that S is an invariant subspace of A. And we've already seen that invariant subspaces, for example, the span of a set of eigenvectors is an invariant subspace. So if S is an invariant subspace of A, then S is an invariant subspace of e to the at. So this is interesting. So that would say that the vectors spanned by the or spaces spanned by the eigenvectors of A turn out to be invariant for the differential equation. So let the initial condition be in S. We're just going to prove this statement. Then we know that it's invariant. S is invariant for A. So ax naught is also in S. And of course, we can scale it by our time. That's also in S. And since this guy is in S, and S is A invariant, we can multiply again by A. So we get A squared. X naught is in S. And of course, we could scale it by the t squared over 2 factorial. That's still in S. So we can just continue this down. We can multiply again by A. Since this thing is in S, multiplying by A, S being A invariant, means A cubed. And then we can scale it in any way, say using t cubed over 3 factorial instead, and that's still going to be an S. So we have that this equation here, if we start out, if x naught is an S, then I x naught is obviously an S. This guy will be an S, this guy will be an S, this guy will be an S. You take the linear combination, the solution will always be an S. So in other words, if we start in an invariant space, or for example, if we start on an eigenvector, or in an eigenspace, we'll always stay in that eigenspace. That's one thing we can conclude. All right, so let's just do a little example. Consider the differential equation, x dot equals ax. The eigenvalues of A in this particular case are 1 and minus 2. So we have one eigenvalue that's in the left half plane and one that's in the right half plane. And the associated eigenvectors are 1, 1 and 1 minus 2. So what do solutions look like? Well, we're going to have, here are the two eigenvectors. Here's the eigenvector associated with the eigenvalue of +1, and it's an invariant subspace. So if we start on that subspace, we stay on that subspace. And notice when we start here, that subspace is actually going to grow. So actually, let me try to explain things a little bit here too that might give some insight. All right, so if I have x dot equals ax with initial condition x naught, that implies x of t is equal to e to the at x naught. Now, suppose that, let's just look at the case where A has distinct eigenvalues. So the geometric multiplicity equals the algebraic multiplicity. Then we can write eigenvectors. Let's see, let me just use a different notation. Let's do eigenvectors. Let's see, let's use t instead of s is equal to t lambda, where t are all the eigenvectors stacked up, and lambda are the eigenvalues. So in other words, lambda will be lambda 1, lambda 2, down to lambda n. All right, so this also implies that, A is equal to T lambda T inverse. So we've already seen that e to the at, we've done this before, e to the at, this is I plus a plus at plus a squared t squared over 2 factorial plus dot dot dot. I we can write as t inverse. A is going to be t lambda t inverse little t plus capital T lambda squared capital T inverse t squared over 2 factorial plus dot dot dot. And then we can write this as t I plus lambda t plus lambda squared t squared over 2 factorial plus dot 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 t inverse. And then this is going to be will be t e to the lambda t inverse. All right, so and where e to the lambda t, this is just e to the lambda 1t down to e to the lambda n t, and zeros everywhere else. Now, one thing we can do, the eigenvectors are inside of here. So let's look at the solution. The solution here, the solution is x of t is e to the at x naught, which we can write as capital T e to the lambda t inverse x naught. So that implies we can write t inverse x of t is equal to e to the lambda t inverse x naught, like that. Dang it. And that means we can write, and so let's let z of t is equal to t inverse x of t. And so that means we have the z of t is going to be equal to e to the lambda t z naught. Similarly, we could say z naught is equal to t inverse x naught. Okay, now look at this equation. This says that, in scalar form, this says z1 of t is equal to e to the lambda 1 t z1 naught down to zn of t equal to e to the lambda n t zn naught. So each of these modes evolve, these are actually called the modes of the system. Z of t here, these are called the modes, and each mode is given by an exponential decay or growth, and it depends on now where lambda, if lambda is in the so if lambda I is in the left half plane, in other words, i.e. lambda I, is some minus sigma I plus j omega I, and this guy, it's going to be in the left half plane. These will appear in complex conjugate pairs, by the way. Then those would be what we call stable modes, because this part of the mode will decay, and if it's in the right half plane, then it's going to be growing. We'll have an unstable mode. Now, if we come back here, notice that when we write it like this, we could also write x of t is equal to t z of t. So in other words, x of t is going to be the first eigenvector. This is an unfortunate set of notation. Let me just kind of do like a bold T1 times Z1 Zn. So it's going to be, this first eigenvector times Z1 of t plus up to the nth eigenvector times Zn of t. So in other words, the solution is, it's going to be this first mode along the first eigenvector. In other words, it's going to be, an exponential decay or growth, whatever, along the first eigenvector, all the way up to an exponential decay or growth along the nth eigenvector. It depends on the mode. And by the way, if these are complex conjugate pairs, the eigenvectors will be complex conjugate pairs. And so the complex conjugate part will cancel out. And that's where you get spirals. So spirals will be given by, in other words, solutions that kind of do this are due to complex conjugate pairs in the eigenvectors and eigenvalues. All right, so, boy, how does this work? There we go. Okay, so we're going to come back to this picture. And in this picture, again, we have the, this is going to be the first eigenvector. So that's like T1. And the solution is writing, e to the lambda 1t. And in this particular case, it is unstable because the eigenvalue is positive 1. And so solutions to the equation, these arrows are showing solutions. If my initial condition is on an eigenvector, right on this eigenvector, it's just going to go out. Similarly, if it starts on this stable eigenvector, it will move in according to e to the minus 2t. So everything's going to be coming along these arrows. Now, what happens if I have an initial condition that is a linear combination of the two? Well, you're going to have a decaying mode along this direction and an exponentially decaying mode along this direction and an exponentially growing mode along this. So it's going to kind of go like this, and will eventually converge out here because this part is decaying. These solutions will converge to this eigenvector. And the same thing for initial conditions here. They're going to converge along this direction but diverge along this direction. So they may converge at the beginning and then diverge. So it's converging faster than it's diverging. So they're going to come in and then kind of go out and eventually approach this eigenvector, etc. So this picture sort of gives you the, what's happening to all possible solutions of the differential equation. This is called a phase diagram. Phase diagram. So it's easy to draw all possible solutions to a second order differential equation, but higher than that, third dimension maybe is possible, but fourth dimension obviously isn't possible. We also have applications to eigen vectors, to difference equations. And let's see. Okay, I was going to add some notes here, but let me just say, let's just kind of move off here to the side. So if I have a difference equation, for example, if I have xk plus 1 is equal to a xk, then with some initial condition x naught, we can find the solution to this differential equation as follows. So x1 is going to be a x naught, x2 is going to be, it's going to be a times x1, which is going to be a times a x naught, it's going to be a squared x naught. And then x3 is going to be ax2. We plug in x2 from here, and that's going to be a cubed x naught. And then x to the fourth is going to be ax cubed, which of course is a to the fourth x naught, all the way down to any, at x at time n is going to be a to the n x naught. Okay, so this is actually the solution to this difference equation, in the same way that e to the at is the solution to the differential equation. Now we can obviously find, we can think about this in terms of eigenvalues and eigenvectors. So if a is equal to, let me just go ahead and write it as s lambda s inverse, then x at time n is going to be s lambda at time n, s inverse x naught, and lambda at time n is lambda to the, lambda 1 to the n down to lambda n. Oh yeah, I should have used k or something. So n is, here, let me just write this as at time k. That's going to be at time k, and that'll be at time k. Okay, so again, we can also, from this equation, we could write s inverse x at time k is going to be lambda to the k, s inverse x naught, and then we let z at time k be s inverse x at time k, and we get z at time k. It's going to be lambda k times z naught. And again, lambda k is diagonal here, so this means that we would have z, z1 at time k, I guess is going to be lambda 1 to the k, z1 at time 0, all the way down to zn at time k is going to be lambda n to the k, z n at time 0. So again, each of these z's is a mode. It's called a mode of the system, and it's given by, instead of e to the e to the eigenvalue t, it's going to be given by the eigenvalue raised to the k. And notice these things will decay if lambda is in the unit circle, or grow if lambda is outside the unit circle. But we can also think of this, if we were to do like a phase diagram, if you have something, again, this is like the first eigenspace, maybe the second eigenspace, and if you had if lambda 1 was, let's say, less than 1, then you're going to move along this vector. And if absolute value of lambda 2 is greater than 1, then of course you'd have an unstable mode. So solutions to this difference equation, would, again, if this is the initial condition, it's going to be hopping, it's going to be growing, or I guess, it's going to be shrinking in this direction and growing in that direction. So what would you do? So you're growing, so it's going to, it might go from here to there, to there, to there, to there, and will eventually converge to this eigenspace, but diverge along that direction, etc. So this is a way to understand difference equations, again, in terms of modes given by the eigenvalues and the direction that those modes are heading in terms of the eigenvectors. I don't know how to get this back. All right. Okay, so that ends what I have to say about invariant subspaces and differential and difference equations.